Okay, good day everyone and warm welcome to this week MIU session. My name is Nico Santop and I am honored to serve you as a moderator for today. And I'm joined by my esteemed colleague Cosmin Delea, an expert in maritime robotic solutions. And he will be delivering an insightful presentation on how robots can help fight marine pollution. Before we proceed with the presentation, I would like to remind everyone that this session is being recorded. To ensure maximum clarity, we kindly ask that the microphones and cameras be turned off during the presentation. If you have any questions or concerns, please do not hesitate to post them in the chat and we will address them at the end of the presentation. Now, without further ado, I would like to turn over the floor to Cosmin. Cosmin, the stage is yours.
Thank you very much, Nico, for your introduction. So welcome, everyone. Today, we're going to talk about the SeaClear project, specifically on the sea trials conducted in Hamburg and in Marseille. So the agenda for today, we're going to have a small introduction round, then about the project, then we're going to jump directly into the trials. So for the problem definition, we have two test sites or two demonstration sites in Project SeaClear. One of them is Hamburg, the port of Hamburg, and the second one is the Dubrovnik area. Both sites have some environmental properties that are, some are similar, so they both have the litter problematic there, but in different nature, meaning that we encounter more in different forms of litter in the port of Hamburg compared to the Dubrovnik area, where we have this common fish nets or litter that comes from people, not from industrial sites. The aim of our consortium is to develop the robotic solution that can be used in both areas and identify, detect, and collect this litter. Our consortium is composed of 4 technical partners, 1 hardware developer, and 2 end users. We have the SeaClear system composed of the following subsystems or components: the robotic system that contains 4 robots, 1 surface vehicle, 2 underwater vehicles, ROVs, and 1 flying or aerial drone. The shore operations center is the application layer that we are developing for commanding and monitoring this system, and it's used for the high-level commands. So we are able to send some specific commands to the robots without directly interfering unless it's absolutely necessary. Then we have the SeaClear service layer. This is the supervisor of the complete system, and it's aimed for delivering the interfaces for end users that require information about the status of the ongoing operation. More insights on the system itself. We have centrally we have a USV, which is equipped with 2 ROVs, so therefore we have 2 launch and recovery systems for them. Additionally, we have another winch and tension control for the aerial drone. This is more for enhancing the capabilities or the duration of operation of the UAV. And lastly, we have the basket, the collection basket, which is actually developed by Frankfurt CML. And this is aimed for depositing the litter that has been collected with one of the RVs, the CROV, the one marked with number 3 on the screen. Okay, I think we have a lot of intro now. We can proceed to the second phase and discuss about the test campaigns. In total, we are planning 6 tests or test campaigns within Project SeaClear. For today's scope, we are going to focus only on the three of them, the one that happened last year in Hamburg and the two that happened in Marseille subsequently in 2022 and a few weeks back in February in 2023. You can see down here the timeline. We are basically in the last mile of the project, and this is why the number of test campaigns, the number of tests increased. For the question why Marseille, it's very simple. We are having all the hardware, all the major hardware components developed in Marseille. Therefore, it's easier to conduct experiments without needing to move the hardware in different locations. Now, for the first test trial, which happened in Hamburg, we have conducted the trials in Lübecker Ufer, which is the company ground of HPA. We've done a series of 6 experiments throughout 2.5 days. The second part of the third day was used for a press conference with live demonstrations. We have noticed during this first trials, by trials I mean the usage of the full system, we have discovered many challenges, and I want to talk about 2 of them today, because we don't have enough time to discuss about all of them. So this is an overview of the experiments that have been conducted. You can see we have done experiments with the USV, we have done experiments with the underwater vehicles, mapping of different litter elements, deploying the collection basket, and also navigation of the underwater vehicles. Now, before we jump into the problems, let me show you first a part of our video that has been taken during the trials. So first we see how the SeaCat has been deployed with a crane to get, and also the basket has been deployed using a crane. It's important to know at this stage that this interface between the basket and the USV has been planned for later on. That's why they were separate. There were tests conducted with the gripper of the collection ROV, and for the deployment, we have tested first time the LARS for the collection ROV. As you can see, or probably cannot see, after deployment, it's really hard to see a lot in water. That's why we rely on different types of sensors for helping us localize the system on the water. Of course, we tested what we could see, the navigation of the surface vehicle. And for underwater vehicles, we relied on acoustic systems, acoustic sensors that allowed us to accurately localize, but also to map the surroundings. In this case, on the left side, you see the bathymetry map. On the right side, we saw the mapping of the underwater vehicles. Yes, the retractment of the ROV can be seen in the last picture, and for media coverage, I think I will skip for now. So I was talking at the beginning of the problems that we incurred. 2 of the main problems were underwater mapping and the collection basket approach. For the first one, as you can see on the left-hand side, we have a 3D map that we would like to construct, in which the elements, the waste elements, are positioned in it. But underwater mapping heavily relies on the quality of our sensors, and the quality of our sensor determines how accurate we position ourselves, and then how accurately we estimate the position of the target, in this case, the waste element. And traditional methods like imagery do not quite allow us, at least from a certain distance, to determine the position of the waste underwater. Therefore, this approach was not useful in Hamburg, or in areas such as Hamburg, where the turbidity levels are high and the visibility levels are quite low. The second important problem was the automatic docking using another classical approach, which is visual surveying. It was really unrealistic due to the same reason. On the right-hand side, you see the view from around 4 meters underwater. The camera is positioned approximately 25 centimeters from the left side of the skid. So we probably can see in this, and this was a good weather conditions, so we can see up to half of meter, which is not really useful if our positioning system doesn't have at least the same precision of 0.5 meters when localizing our system underwater. Besides, we notice we need a compensation for underwater localization accuracies on two axes. We only focus on one axis, the x-axis, whereas we notice a lot of tilting problems due to the hydrodynamic effects and this small collision, so to say, between the collection basket and the ROV trying to deposit waste in the basket. That's why we needed to try something else, which has a bit more softer approach and also compensates on both Z and the X axis. Now, moving on to the second trials we did in Marseille. We had a very packed schedule, as it can be seen, for the full week. We addressed both of these problems, and namely for the underwater mapping. We used a different approach, which was not possible with the current sensor that we had in Hamburg, but it got us an understanding of the problems that we have with our sensors. Namely, we used position estimation with aerial vehicles. So on the right-hand side, you see the tracks. The white tracks are the ground truth, the real estimation of where the ROV was, and the green line is the actual measurement. That in turn had an effect on the position where the targets were estimated in the bathymetry map shown on the left-hand side. How could we do this? Well, simply because the water quality in Marseille was sufficiently good enough for us to target the ROV with aerial vehicles. We could do this experiment, and we could realize that the performance of the USBL system that we used was not really great, 3 to 5 meters. And this is not because the sensor is not good enough, it's because it's not suitable for the environment that we are using it. So it's usually more for deep water than for shallow ones. For the approach, we added a different funnel, which was a 2D funnel. So we have the approach that the tolerance that increases the tolerance, the compliance on the x-axis, but also on the z-axis. These can be seen on the right-hand side. It had an impact. Of course, in the right-hand side, you see a smaller version of the z-axis of the funnel, which has been then extended in another video, but I don't have it right now. But you actually see here how the funnel is actually helping the ROV compensate for the errors of the position. Furthermore, we could actually see that the visual surveying, the tracking itself is really good, but nevertheless, we need this kind of compliance mechanism even in clear water scenarios. Okay, third test campaign that just happened a few weeks back. We had a replacement of the USBL for the underwater mapping. We had the replacement of the USBL with an SBL solution, so a short baseline, which increased performance and had a standard deviation of approximately 1.3 meters that can be seen on the right-hand side. So the blue tracks are now the ones with completed or done with the underwater equipment, underwater sensors, and the yellow, orange ones are done by the UAV. We see some shifts, so some of these peaks here, but nevertheless, overall, we have a quite lower deviation, which translates in better performance of the pose estimator and in terms of the mapping. So it affects the whole cycle. Also, as an example of how this has been done, a small video. So you see on the top you have the ROV underground. On the lower part, you have the tracking done by the UAV. It's important to know that this is possible only when we have a bit of visibility, because the underwater vehicle needs to be submerged under a certain area level, so that we are able to get not so noisy results from the acoustic equipment, and then interpolate the data we have with the one obtained by the aerial vehicle, and then overlap these two graphs and see the performance. So it's a kind of a trade-off, if you want to call it. The higher we get, the closer we get to the zero level, the noisier the results are of the underwater equipment, but the easier it is to actually pinpoint on the ROV using classical imagery. This is a typical trade-off that we have to deal with. Furthermore, what we've done in the last test campaign, we have fused the RTK GPS, which allowed us to have more coherent overlays on the bathymetry map that we constructed before the trials, so onto which we have the waste deposited in a 3D map, which is further on used for the collection part. Lastly, for the approach, we increased the area of the funnel so that it has a three-dimensional space, and it actually helps on all three axes, X, Y, and Z, for the compliance mechanism. You can see the funnel painted with the red color on the left-hand side, and these indeed helped us to have to overcome the limitations of either the pitch control on the ROV or the inaccuracies of the localization system, because still 1.3 meters is still a lot for the kind of approach we need. And as you can see on the right-hand side, I mean, it's hard to imagine because just a picture, but the approach was really, really more stable compared to the previous attempts. Now, I think this is my last slide. Yep. So, yeah, these were the trials that happened in Hamburg and in Marseille for the SeaClear system. If you have any questions regarding the technology that we used or the trials, feel free to raise them either in the comment sections or directly through your microphone. Thank you.
Thank you, Cosman, for the enlightening presentation. Once again, to the audience, if you have any questions, please feel free to ask them in the chat or unmute your microphone. In the meantime, I have a question to pose. In this use case, it's very important that the robots can communicate to each other. How is it possible?
Yeah, this is something that has not been covered here, indeed. Well, let me go back first to the picture with all the robots, just to, yeah. So as we can notice in this picture, we have all the systems connected to the ship, to the USV. The USV in this case acts as a remote station, if you want to call it, or as a universal communication interface through all the other systems. That means we are connecting directly through the USV and tunneling ourselves towards communicating with the other vehicles. This is done also within the ROS framework shown here. So as long as there is an Ethernet connection between the shore center and the CCAT USV, we can basically connect and get any data we need. Apart from that, we can also send data, of course. The only thing we have to take in consideration is the bandwidth that we have, because this is something, especially if we have a lot of video streams, as we saw in some of the videos, it's easy to saturate the flow of data and reach the maximum throughput of the wireless network that we're using. That's the most concerning aspect right now in terms of transferring video data. That's why most of the processing is done on board.
Okay, thank you. So we have more questions from the audience. So the first question is, what do you think is the biggest challenge you're still facing before you are able to commercialize this idea?
Very interesting question. Well, there are many challenges, as I pointed out two of them. Maybe I'll go to that slide. There are two big problems that we have, or we have fixed, but not completely. We're still needing some validation tests for confirming that everything is working perfectly as we want for the Hamburg use case, especially. For the others, not that much. So we have some technological limitations, but the biggest challenges are, first of all, increasing the level of autonomy. This is something that needs to be capable to work in unstructured environments. So it needs to first navigate safely, it needs to target the waste elements, and then if there's a current, it needs to be able to remap and grasping. There are a lot of things that are very, very thin-haired. That's why the precision needs to increase way more than the actual technologies that we have in order to have this high level of autonomy. Secondly, I think it's a matter of finding end users that would require such a system. My belief is that the system can be commercialized in form of a service once the problems are solved with accuracy and with autonomy. Nevertheless, it will need maybe some more attention from possible end users. I'm speaking now of port authorities or maybe marinas that might need this solution and are not right now looking into this direction. So it's a matter of attracting their attention and having the trust that this system can be really beneficial for them.
Okay, thank you. The next question is,
Sure.
can you give more information about localization of the ROV underwater, how it's done?
Mm-hmm. Sure. I'm not sure if I have. Maybe I will go to this slide. So I talked about the SPL. Basically, we have these devices that communicate with each other using acoustic waves. Based on the time of flight principle, we can determine what's the distance from our target emitting the signal and the receiver that consumes the signal. Now, like similar to GPS devices, the same thing happens on the water, but with acoustic waves, because in comparison to electromagnetic waves, acoustic waves are not absorbed that strong as like electromagnetic ones. So based on the time of flight principle of the sound wave and interpolating multiple measurements coming from the same source, but received on or consumed by multiple receivers, we can do the triangulation of the data and therefore accurately determine where the target is, the emitter, in a 3D space relative to our own position. Now, this is the first step. This is the most important for robots because we work in local frames. Then the second step is adding on top the global reference system, which is usually done using GPS or RTK GPS, meaning that from this XYZ position, we have to give it a meaning. What does it mean in the test site that we have? What's our latitude or longitude and okay, the depth will be the same, but latitude and longitude will differ. I hope this answers a bit. It's a huge field, so I think it's hard to summarize it, but I think this is the main principle of the localization system we are using. Both USBL and SPL, they work on different frequencies. They have a bit of a different principle of how they consume this data, but the idea of interpolation of acoustic sound waves based on the time of flight principle is the same.
Okay, thank you. The next question. Did Fraunhofer develop the ROVs and USVs in-house, or have you adapted drone technology developed by other companies?
Neither. So neither of those two. We have this 4 robots, which are here. So the 3 waterborne robots are developed by a company, in the subsea tech company in Marseille, which have the basic functionalities like remote controlling them towards, or maybe giving them a waypoint. This is absolutely insufficient for the use case we have. That's why all the sensor fusion and control loops, so the software part, has been developed also at Fraunhofer, but also among the other partners that are participating in this consortium. And regarding I think it was the drone technologies, of course, you don't reinvent the wheel every time. So I'm sure some components are highly standardized, and some of the software packages are available to multiple, are used generally by multiple users. So I don't think we'd reinvent the wheel in terms of navigation, but the greatest innovation that we bring here is the capability of targeting waves, which is not the biggest data set one would find over the internet. And that is one of our goals, and we created this data set for marine litter. And also having a distributed or collaborative control for underwater vehicles for mapping underwater elements and grasping is something that has not yet been done, especially with autonomous vehicles. So that's, I'm probably going a bit beyond answering also innovation, but it's not, the point is not none of the 2 options are the case here.
Okay, thank you. So we have more questions. I will choose 2 of them. What will be the approach to oil and chemical pollution, not just garbage?
Oil spills are something that is a very researched field right now, and there are solutions for oil spills. There are more interesting solutions coming up. What's important to know is that the SeaClear project focuses on underwater waste that can be grabbed, which is, of course, in environment which has vertical currents, the oil spills indeed mix on the layers, within the layers mix between water and oil, and therefore a specific approach has to be used also underwater. It's a very interesting topic, and I think it deserves an attention from the robotic developers or like ourselves, but it's not something that the SeaClear project will be able to do at the end. With some adaptations, and I'm thinking now maybe on surface collection based collection of sampling the water and basically creating a filter that can be already implemented, I would say, on a surface vehicle. One could adapt the solution for this problem. Nevertheless, because it's a project that requires innovation, we had to lay focus on things that are not yet being developed or not yet being done. That's probably the reality why we haven't looked into oil spills. There are also other adjacent subjects, oil spills, such as mines, and in some parts of the world, also in Hamburg, we have this problematic. And we thought of how to approach this problem. It's possible. Nevertheless, it's out of scope of the current project. It's something that we have to look forward when we identify our potential clients and their needs.
Okay, thanks. So the final question, and then I think we are done.
No problem.
Don't stretch too presentation that long. It's a follow-up question. So, are you planning to relying on other technology channels to deal with more polluted areas? Do you think this is possible to implement within the time frame of the project?
No, but the question is very good actually, because this opens exactly the
Husband, you are somehow muted.
Sorry. Sorry. So let me repeat. So the question is actually really interesting because this opens up the SeaClear 2.0 project, which is a continuation, an extension to SeaClear 1. And one of the goals there is to extrapolate the usage of SeaClear 1 system to a larger area or larger use case in which we have bigger chunks of waste, which currently cannot be collected with a SeaClear 1. So in some parts of the world, also Hamburg including, the number of bigger waste elements that have a bigger mass or bigger volume, it's much more predominant. Sorry. That's why we want to create a system that is of a more general use case. And secondly, we also want to raise awareness of the problem itself because we are tackling the effect with the SeaClear 1 or SeaClear 2 project. And this is something we want to look into the SeaClear 2 project and handling more the social aspects of this global problem, which is marine waste. And for that, we're going to organize workshops, we're going to organize groups of discussions, and many more. And this is something we just started, and we're going to keep you updated next time on the SeaClear 2 update, but it will be out of scope for SeaClear 1. But thank you for the question. This was really a good launch pad for the next project.
Okay, thank you. So we hope you have enjoyed this week MIU session, and please note that we will be back in 2 weeks with another fascinating topic. And to all of you, thank you for your attention and for joining us today. And have a great weekend, and we hope to see you next time.
Thank you very much. Have a nice weekend.